So anybody that's not here will have it to get caught up. And you should be making the 3 diagrams. Let me see, I'm gonna randomly pick on Dante. What should this box be?
I made it fully purple.
And what does the purple represent for you? Potential energy. This box should be one color. It doesn't matter what color. But then you need to make a key on the side that says that one was potential energy, huh? Let's see who's next. It seems to be Antonio. Can you tell me what this second box should be like? And what do those colors represent for you? So it's half potential and half kinetic? That's exactly right. When it's halfway, it's 50-50, isn't it? If it's not halfway, it's not 50-50 though, is it? It might be 75-25, or it might be 25-75. Yeah? But this said, well, we're going to assume this is halfway. So it should be 50-50. Lastly, I have Jonathan. What about the bottom one? For what? What kind of energy should it be? It should be 100% kinetic at the bottom, right? Now, the next thing you have to do, you've done one color at the top, you've done a half and half in the middle, and all the other color at the bottom. You've made a key on the side that says those colors are potential and kinetic, correct?
Yeah.
Now you have to justify that. Down here where it says justify your reasoning. So what I mean by that is I want you to explain what you've done. And I will give you a hint. Do you think it would be a good idea to use the law of conservation of energy in your explanation? Did we see any energy destroyed or created? How can we tell that none was destroyed or created? Well, because the boxes are the same size, aren't they? It's the same amount of energy, total energy, isn't it? But did we see energy changed? Right? So could you use the law of conservation to justify your diagrams? Okay, I would like you to do that now. Yes, sir. Yeah, did you already finish this? Okay, take your pass, leave your phone. You guys that are done, did you explain what you did too? Did you make a key? Hey, if you want to, you're in this class and let's say you've done all the work that we've done in class on your project, done all the pages with me that I've done with you. But let's just say, of course you wouldn't do this, but let's just say you didn't do any of the stuff that I said to do at home. Should you turn in the project incomplete? No. Should you not turn in the project at all, ever? No. Should you finish it and then turn it in? Yeah. Obviously, that's your number one choice, your best choice. But what's a better choice, to never give it to me or to at least give me what you did in class? Right? If you're not willing to do any of the work at home, or you just know it's not going to happen, at least give me what you did in class, right? So I want to give you some points. I might not be able to give you all the points, but I'd rather give you some. Okay? And I'm going to pick on Mr. Lackey and just point out that when I'm talking with the group, I expect your ear canals to be vacant, except for the energy from my voice. Thank you. Anybody else have earbuds in underneath their hair or something? Natalia, are you hiding it under there? Oh, she really was too. Yeah. Girls think they can get away with anything, don't they? All right, so we're actually going to do something different before we go to the windmill. Okay? Please go back to page 10. Here's page 10. So before Halloween, I believe that we filled in these boxes, didn't we? This one was just the same as the monkey, wasn't it? 100% potential up here, 50-50 down here, and 100% kinetic down here, correct? But then the tricky part was the bounce, where some of that energy was lost to these three different kinds of energy. Elastic energy, when the ball flattened a little bit and then bounced back, huh? That cost it some energy. Was that energy destroyed? No, but it was lost from the ball, wasn't it? Same thing, there was some energy that went to sound, correct? And that energy was lost from the ball. Similarly, there was some heat energy created by the friction of the ball when it hit the ground. And that thermal energy, that heat energy was lost, right? And so then it bounced up. We should have it being kinetic down here as it's leaving the ground. Since it's on the ground, could it even have any potential energy? If this is the ground and this is the ball, when it's on the ground, does it have potential to fall any further? No, it's on the ground. It can't fall any further. So this diagram must be showing that it has only kinetic energy just at the beginning of its bounce back up. And then this diagram, it's kind of half and half, isn't it? And then at the top of the bounce, it was fully potential again, correct? But what we didn't do, we did the coloring, but we didn't do the math. See these equations where it says PE equals KE equals ET equals? That means ET means total energy, E sub T. So we have to do some math, right? So, we ready for page 10? So wait a minute. If I'm supposed to calculate the potential energy, what equation do I use for that? If I'm going to calculate potential energy, do I have to memorize that equation? No, I don't, but I have to remember how to use it. There it is right there. Well, it's on your paper. You can see where I circled it, can't you? Yeah. So use mine as a guide. You might not be able to read it up here, but you can tell where it is, huh? Yes, sir. Let's figure that out. First of all, what's MGH stand for? M is mass, G is gravity, H is height. So that was a really good question he had. You can't solve it without knowing the height, right? And you are going to need a calculator at this point. Whether it's your phone or the one on your computer, it doesn't matter. But notice right here in the corner, it tells you the mass of the ball, doesn't it? The ball mass is 0.7. So put that in your computer, in your calculator. And you might have already remembered this. I don't think you have to memorize it, but we use it so much, it might make it quicker if you do. Gravity is 9.8. So you're going to take the mass of 0.7 times gravity of 9.8 times the height. But let's use this, let's just say that this is meters high right here. So where did it start from? 100 meters high.
How did they get it up that?
600.
They climbed a tree. They went up a cliff. Yes, yes. Yeah. And erase those because we're going to calculate joules instead of percentages. These would be correct percentages. We're going to talk about joules. Okay? Yes.
Rewrite it down.
Yeah, and you should put your final answer down there. PE equals, and if you're between 500 and 1,000, you're correct. I'm not going to tell you exactly what it is, but it's in the 600s, right? Okay. And then what did we what unit of measurement did we use? So you should say whatever your answer was with J at the end for joules, huh? Right? So to find potential energy, we have to multiply mass times gravity times height. Here's the mass. 0.7. Here's gravity, and here's height. 100. 0.7 times 9.8 times 100. Hey, what's the kinetic energy there? Do we have to do math or do we just know? If the ball is waiting to be dropped, it's not moving. Kinetic energy is the energy of movement. So if it's just waiting to be dropped, we know that the kinetic energy must be 0, right? 0 what? Still joules, still 0 joules. And what's my total energy then? PE plus KE equals the total energy, whatever it was, whatever the potential was, 600 and some for our total energy, huh? Good with that? Let's look at the next one, but be careful because it's giving you a more precise measurement. It's not exactly 50% of the way down. How far down is it? Yeah, it's 48% down, isn't it? And let's look at the way this is measured. Here's 40, correct? Here's 40. How many lines do I have until I hit the next number? What's it counting by? Is it counting by fives? Let's see. 40, 45, 50, 55, 60, 60. Wait a minute, that didn't work, did it? It's not counting by fives, it's actually counting by fours. So be careful when we read this later. Here's 40, 44, 48, 52, 56, and 60. So each little line on this graph is equal to 4 meters. Okay? So be careful on that. A little surprising they set it up that way, but that's the way they did it. So what do we have to do now? Well, it's 48% above the ground, right? Doesn't that mean that it still has 48% of its kinetic energy left?
Yeah.
So plug in your calculator. 0.48. We're going to take that 48% and we're going to convert it to 0.48. I just divided it by 100. That's what percent means. So 0.48 times, what was your total energy before? 0.48 times your energy from earlier equals, that's how many joules you should have of potential energy. It should be about half, because 48 is pretty close to half, isn't it? Sounds like it's about half, huh? Yeah. Yeah. That is potential.
Okay, that's the potential.
This one is potential.
Okay.
Yeah, because it's 48 meters above the ground. So it should be a little less than half potential and a little more than half kinetic at this point. Yes. Okay, guys, let's skip kinetic for a minute. What's the total energy? According to the law of conservation of energy, it must be the same as what we started with, right? So you can fill that one in right away. You could even fill it in down at the next one too if you wanted to, because that total energy remains the same. Can't be created, can't be destroyed. Now let's go back to this halfway point. What should the kinetic energy be?
356.7.
whatever the number is, how did you find it? This is how you help one another. If you're stuck on something and you ask your friend for help, and you just write down 356.72, did you figure out how to do it for yourself? How are you going to do it on the test? Are you really helping yourself by doing that? I don't think you are. I would argue that it's easy for you to copy somebody else's work, right? But it's to your benefit not to. For instance, am I just giving you the answers here? Or am I helping you figure out how to get the answers for yourself? That's what you should do for your friends too. And if your friend just wants to give you the answer, you should say, well, tell me how you got that answer. Because that's what you need to know. So Joseph, how did you get that answer?
I figured
Okay.
I'd subtract 28 from the 6.
That's what I wanted to hear. How did you find the kinetic energy? Well, you know that the total is when you add those two together, isn't it? So if you know this one, you just subtract to get the other one, huh? Let me give you a simple example you can do in your head. Let's say the total was 25 joules, and of that, my potential was 10 joules. How much must be kinetic energy? It's got to be 15, doesn't it? Why does it have to be 15? Because 15 plus 10 makes my total of 25. Right? So this is just a little more complex number, but you just subtract to find the kinetic energy, huh? Are we good with that? Yes? Hope you're up here. Kim? Hang on a minute, okay? I want to finish this page first. Now down at the bottom, this one should be easy. You don't have to do any math. What's my total energy? The same as I started with, right? When it hits the ground, when it's on the ground, if this is the ball, when it hits the ground, how much potential energy is left? No potential energy, huh? And if there's no potential energy, how much of it is kinetic energy? All of it, right? So this should be a review of what we've already done. How many times now? 10? Right? Now the tricky part, the bounce. So for the bounce, to begin with, I want you to once again carry over the total energy. So the total energy stays the same at the bounce. So go ahead and copy that. And this is the reason right now that we're not calling it mechanical energy, because it's not all mechanical anymore. When it hits the ground, some of it turns into sound, and some of it turns into heat, and some of it gets squished and released into elastic, right? So we lose this energy from the ball. I'm hoping that you've already filled in this little phrase down here. We actually did that last class. What happened to that energy? Yes, it was transferred out of the ball. Was it created? Was it destroyed? No and no. But the ball lost it, huh? In what forms did the ball lose it? Well, it says right here, doesn't it? Elastic, sound, and thermal energy. How much of each of those? Look closely. How much elastic energy was lost from the ball? Yeah. Doesn't it say right there 72 joules? How much sound energy was lost from the ball? 57. How much thermal energy was lost from the ball? Right? Now, if that energy was lost from the ball, what are we going to do with it? We had its total energy, but then it lost this. So what do I do with it? Let's work a simple example. Here's a ball, a roll of tape with 100 joules of energy. It hits the ground and we hear it. It just lost 10. What's left? 90. It squishes a little bit and bounces back. It just lost another 10. What's left? 80. It also heated up the ground a little bit. 10. What's left? So what did you do to find those answers? You just subtract them. So please take your total energy and subtract those three types of energy from it. Take your total energy, subtract these types of energy from it. What do we get? I'm guessing you're gonna have around 500 some. And all that energy is left in the ball, isn't it? That 500 and some joules is left in the ball. And now the ball is moving. So this is actually all kinetic energy now. Are you with me on that? But the ball hasn't left the ground yet, so how much potential is there? 0, right? So to do that again, if you take the total, 600 and some, subtract these three from it, that gives you the kinetic. And there is no potential left, huh? Now here's the tricky thing too. Go up to the next one. What is our new total energy for this one? Is it still 600 and some for this one? No, because the sound and the heat and the elastic energy were lost, correct? So the total energy for this one should be equal to the kinetic energy of the previous one.
What's the total energy?
The total energy for the bottom one is still the same as it was on the left side when you include the elastic, sound, and thermals.
Yeah.
Or I could just take a picture. Hey, you got any tissues? My nose is bleeding.
I don't know. Like I said, this isn't really my room. I have these. Do you want one of those?
No.
Then you should go to the restroom. There's paper towels here. Sufficient?
My sword is bloody hand. There's blood on my sword.
Okay.
Stop touching things.
So, where were we? We're on this one, aren't we? Yeah? And we figured out that its total energy was the same as the previous kinetic energy, right? It should be 500 and some. This is going to be the hardest one to do. So here's what I'm going to do. I'm going to draw a line from the center of the ball over to this measurement on the side. So how high is the ball now?
63.
Remember what we're counting by over here, right? We're counting by 4s, aren't we? To me, it looks pretty close to being halfway between 60 and the next one, which would be 64, which would make this what percent here? 62. That would be 62, huh?
Do the calculation. I'm not going to do a copy for mine. 536.
Are you good with that? You see how I got 62? Okay, so now take 62% of the total energy. How do we do that? Take 62 and change it to 0.62. Multiply by that total energy. And is that going to be potential or kinetic? Let's think about it. This is being just measured from the ground, isn't it?
Potential because it's more than.
It's potential because it's more than halfway up. Huh? So you should have your bigger number should be potential now for this one. And how do you find your kinetic? Exactly. Once again, we just subtract. Total energy minus potential is gonna give the kinetic. Are you with me? Okay. So 0.62 times the total is gonna give our potential. Take that number, subtract it from that same total, and that gives your kinetic. Go ahead and do that. And that's the hard one on this page, I think.
We're still going on the middle, right?
This is the middle one on the bounce, yeah. The top one on the bounce should be easy. How much potential at the top? How much kinetic at the top? Remember, it's bounced up and it's kind of pausing in midair at the top of the bounce. Is it potential for it to fall back down? Yeah, so it has a lot of potential energy. Is it moving though? Kind of paused in midair. So how much kinetic? It's actually reversed direction, hasn't it? So there's a tiny moment in time when it stops. And it has no kinetic because it's not moving there. So just like you've drawn before, it should be 100% potential and 0% kinetic. And those two added together should give this total again. One more thing I want you to do though is tell me what percent of the bounce of the original height did it make it to? And I drew a line across there to help you figure it out. So fill in this percentage over here. What percent is it? What percent is that? Actually, it's a surprisingly high percentage. I don't think it's real. No. Just write it down and I'll tell you if I agree. How about that?
Wait, hold on.
I totally agree. Do you think a ball normally bounces back that high? That percent of its original drop height? Did any of yours bounce back that high? So when you did the 2 meter drop, it would have bounced back that high to be that same efficiency, we call it. That's a very efficient ball. If it can make it that high back, we would say it's 90% efficient. Okay, are we good? All right, so I had asked you to finish this page 11 by yourself for homework, right? I want to remind you that you're supposed to highlight the text. Probably something important in every paragraph, huh? You're supposed to answer these questions, fill in the blanks. Then I wanted you to do this page on your own. And I've seen confusion on this, so I'm just going to show you again what I wanted you to do. Highlight the important text. So I'm going to go down to stage 1 down here. And I'm going to highlight that in stage 1, energy is lost due to air resistance. When the ball collides with the air molecules, both the air and the ball are made a little warmer.
Right, it's fine.
Over here, I'm going to show what that described. Did you do this too on yours? I'm going to show that some energy was lost here. Now, have I taken what that first description was and added it to the diagram? I used arrows and labels to show that. You need to do that same thing for stage 2, 3, and 4. Does that make sense? What I want you to do? Okay. And that takes us back to this page. And we just did the monkey together, huh? The monkey should have just looked like exactly like any falling ball that we've studied. Starts out all potential, then it's 50-50. It ends up all kinetic, huh? But this is not the only kind of energy conversion. When something's falling to the ground, it's not the only energy conversion we want to look at. So we're going to look at two other ones that don't involve something falling. Starting with generating electricity using wind power. So this is where we are now. So tell me this, what is wind? It is air, but what is the air doing? Wait a minute, if it's moving, then it has what energy? It has kinetic energy. So what we're doing with a windmill, with a wind turbine, is we're trying to trap that kinetic energy. And we're trying to convert that kinetic energy into electricity. And it takes a series of steps for these conversions to occur, right? And of course, energy can't be created or destroyed, but it can be converted, huh? So to start with on this one, all the energy is going to be kinetic. I think I shall use this color for my kinetic. Now you should use the same color that you used for your monkey because you already made a square for that, didn't you? I like using control paste. So makes it way faster for me to do things like this when I have to do one box after another. So what was this? This was, oh yeah, kinetic energy, right? That's step one. It's all kinetic energy, moving air. I think I shall label this too, and you should probably label anything that I label. What about down in the next one? Inside the wind turbine, there are a bunch of gears. And so the blades of the wind turbine are moved by the wind. And then those blades move the gears inside the turbine, huh? But wait a minute, if I'm talking about moving gears, they're spinning around, what kind of energy is it?
Kinetic.
It's still kinetic. Have we converted the energy from one kind to another or transferred it from one object to another? We've transferred it, yeah. Do you think that was 100% efficient or were there some energy losses along the way? Absolutely some losses. So I'm going to make it be this big for my kinetic. In what forms do you think energy was lost? Think about how we lost energy during the bounce. Do any of those apply? All bounced. It lost energy 3 different ways. I think 2 of them apply here. Would this create some friction and release some heat? Would that cost us some energy? Yeah, that would. So I need to add heat energy or thermal energy here. I'm just going to have one box to represent this. We're not going to measure it. We just need to. There it is. And of course, if I have a new type of energy, I have to add it to my key over on the side. What was this? This was heat or thermal energy, huh? I think those two terms are pretty interchangeable, so I'll use them both. What else do you think we might have lost energy to? Do you think there'd be some sound made by these gears spinning around and grinding against each other? I do too. So the other big loss of energy here is from sound, which means I need yet another color. Put that down there. I have to add it to my key. And then what happened to this energy? Is it still in the system or was it lost to the air? The heat and the sound. That was lost to the air, huh? So I need to make a note of that. I'm going to draw an arrow first of all, showing that these are lost. Which means when I go to fill in the last one, will I fill in all 4 of these boxes? No, because I've lost that top box, haven't I? Which means my final energy is only going to fill in these bottom 3. What kind of energy is it that I'm trying to get here? What's my goal? Yep, I need electric energy. Let's see. But you know what? Is that really my final goal according to the diagram? I'm going to use black for that. So in this case, you guys know that electricity is kind of lost as it's traveling along a wire. And that's why they make some wires of different sizes. The thicker the wire, the less loss you have. Called resistance. Maybe you've heard of that in electricity, resistance. And they can measure it. They measure it in ohms. And so there is some electricity that's lost. So I'm going to show electricity here as being lost. What else do you think might be lost? Actually, I have to do it down here. What else is lost from this light bulb? Light is not lost. Light is what we want. So I'm going to have that be. Absolutely. Does the light bulb warm up? Yeah. So this is going to be what I really wanted to get was light. But there's one more loss. Oh yeah, somebody already said what it was, huh? What's the other loss of energy? Was heat, correct? So when you're done with that one, it should look something like this. And once again, we have some more energy.
Why do we have heat twice
Yeah.
on your key?
Oh, do I have heat twice?
Yeah.
Oh, I'm sorry. I forgot that I'd used it already. Thanks for catching that. This one should be the same as the previous one, shouldn't it? And I never made kinetic energy, so I'm just going to change this one to kinetic energy.
Yeah, you didn't make kinetic.
Oh, I didn't make potential, huh?
Oh.
There we go. Because I didn't do the monkey one. I didn't have any potential yet. So look at this. How much energy in terms of these boxes was kinetic to begin with? Weren't there 4 of the boxes kinetic to begin with? How many of those boxes ended up being light? Only 2 of them ended up being light, right? So what was my percent efficiency? I wanted it to be light, correct? So wasn't my efficiency only 50%?
What does the black say?
The black says electricity, yeah. And once again, I'm gonna ask you to justify the diagram, explain what's going on. Justify your reasoning for showing this diagram like this. Starts out all kinetic with the wind turning the turbines. Some of that kinetic is passed on and transferred to the gears. Now they're turning and they have kinetic energy, but in the process they lose energy from sound and from heat, from the friction. And then this is used to make electricity. And then that electricity is used to light up the light bulb, but some of the electricity is lost both to heat and just due to electrical resistance as it's going from the power plant to somebody's house. So we only end up with 50% of the wind energy actually being converted to light. And it's amazing to me, but that would be actually a very efficient system. Like a car, the efficiency of the energy in gasoline that you burn to move the car is something in the range of 10 or 12% efficient. That's a good question. If it's an electric car, I don't know the answer. I'm talking about a usual gasoline burning car. I mean, think about what temperature does the engine end up after you've been running the car for a while?
Pretty hot.
Really hot. Where did that energy come from? From burning the gasoline, huh? So did that gasoline move the car at all, or did it just heat up the engine and then it was lost to the air? Then there's friction between the road and the tires, huh? So there's all kinds of losses of energy along the way. We don't have any systems that are 100%. Most of them are pretty low. I really like that electric car question. And you would have to be careful in the way you answer it. Because to be honest, wouldn't you have to start with the energy in the wind, for instance, and see how much of that was converted to movement along the way? It wouldn't really be fair to see how much of the car's battery got converted to movement, because it took energy to charge the battery. So how efficient was that part of the system? Should be included in any accounting. Ready for slingshot?
Oh.
So explain what happened there. And we'll move on to the slingshot. I want you to think about what kind, if you're ready for the slingshot, before we begin, I want you to think about what kinds of energy will be involved. What kind of energy is going to be involved in that slingshot system? Definitely elastic energy. What else? Yeah, this is good. But hurry. Leave your thumbs. Definitely elastic energy. What else? What are we trying to do? What's the goal of the slingshot? To launch a rock, for instance, right? So what kind of energy are we trying to end up with? It's moving that rock, isn't it? Our goal is to have movement. Yeah? But are there some losses along the way? Yeah? True enough? Yeah? Would there be a little bit of loss of elastic energy? A little bit of loss of sound energy,
Yeah.
a little bit of loss of heat, maybe, right? Which is what air resistance actually does, is creates heat. It's friction. So, here we go. Are you ready for the first one?
No.
Well, if you look at the first one, it's not stretched out yet. So we don't have any energy in the system to begin with. If you need to come back to your justifications, you can do that. But we should move on to finish the slingshot together. And you can explain what's going on your own time, if needed. To begin with, the slingshot doesn't have any energy in it, does it? Then, what kind of energy have I added here? Yeah. So I need a new color, it looks like. Oh, wait, did I have any elastic anywhere else? No, I didn't. So I need a new color.
Did we have elastic and half potential?
Okay, I didn't want to go here, but since you asked, elastic energy is a type of potential energy. So there's gravitational potential that we mostly talk about. Then there's elastic potential, right? It has the potential to move, doesn't it? Right? But not from gravity, from the elastic energy I put into it. So I'm not really going to differentiate between them. We're just going to call it elastic.
Yeah, no.
Second one's.
Let's see, then I need to add this over here. This is going to be my elastic energy. I stretch it out, right? And what does that elastic energy get turned into? Yeah, it turns into kinetic energy, huh? Do you think it was 100% efficient? No, that's impossible. So here's some kinetic energy. Let's see, what kind of energy was lost? Sound. What else was lost? Yeah, and heat. As usual. Okay. So something like that, and then explain what happened down in the bottom. Justify what happened.
What's your green?
My green was heat, I believe. Or was it? No, green was heat. Yeah. You just label it as having no energy yet. It's just the slingshot sitting there. So we're going to leave it blank, but we need to explain why we left it blank. So we wrote no energy yet to begin with the top one. Do you think that NASA engineers need to know how to do this kind of stuff?
Yeah.
Do they have to be able to calculate energy conversions?
Yeah.
Absolutely. What about an engineer for Ford? Someone designing a car, do they have to know about energy conversions? and do calculations about them. Yeah, so what we're doing is really related to engineering. There's a lot of good jobs in engineering that pay pretty well, better than teaching.
How are you an engineer?
I liked teaching. Besides,
July.
did it? Would an engineer have July off? Yeah, an engineer probably gets 2 weeks off every year. But I probably work more weekends than they do. No, that's not true. It used to be that if you retired in Nevada, that your healthcare was covered for life, but they don't do that anymore. Yeah, things aren't as good as they used to be in that sense, healthcare. Like, I don't know, did I tell you I retired already and then came back? No? Yeah, it's true, I retired. And then I came back to Incline because they needed another science teacher. And I'm like, what, Incline? Where I started my career in the 90s? Yeah, I'll come back. So I came back. But during that year that I was retired, I had to pay like $1,000 a month healthcare for me and my wife. Yeah. Healthcare, in my opinion, is really messed up in this country.
Oh, yeah. Agreed.
Okay, how are we doing? Are we done with the slingshot? Are we done with page 13? So what do we have? Only 3 pages left, huh?
We gotta justify our reason.
Yeah, you gotta justify your reasoning.
How about this kind of be blank forever?
Yes, because there's no energy in it. Does that make sense? Why we would leave it blank if there's no energy?
Oh.
So it's like this rubber band laying here on the table, huh? I haven't put any elastic energy into it yet, have I? But as soon as I pick it up and stretch it out, now I added energy to it. But where did that energy come from? From my muscles, huh? Did you justify?
I'm thinking of what to write.
That's a good plan. You gotta think about what you're gonna write first, huh?
You know how this is a multi-page project? Not a good idea with you.
Hey, I thought some of you might wanna come see me to, correct mistakes on your test or something. But not very many people have made that decision to invest that time in raising their grade. Again, that's up to you, isn't it? Like I was talking about earlier, it's your responsibility, huh? That's what I mean by you create your grade. If you don't do well on a test, should you just leave it and live with it? I don't know, that's your choice. I'm just giving you the option to making it better, but you have to come see me to make that happen, right? Okay, so this page was titled, Let's Practice with Models, with energy models, which were these diagrams, huh? And we started with the usual model of something falling, but then we had stretched beyond a falling object to energy conversions in other situations, huh? Yeah? Really, we're mostly gonna stay focused on falling objects, but I want you to know that you can also do all kinds of other energy conversions using this same approach and following the same law of the conservation of energy. All right? So this page, let's practice with models, two-dimensional diagrams. Next page, let's practice with math.
Yeah,
Yeah,
more math.
I told you this was engineering. Yeah. So to start with, I want to point out a couple things that you should know how to use these equations, although you don't have to memorize the equations, do you? Right? But you have to know how to use them, don't you? Right? I'm going to give you these on the test. Probably next week is the goal. Here's my two goals for us. Number one, finish this project by Friday. Number two, take the test at the end of next week. I have a couple other practice assignments that I think will really help us get stronger for the test after the project. We have to do those, then we take the test, okay? On the test, I'm going to give you these equations. You don't have to memorize them, but you have to know when to use the right equation, and you have to know how to use it, don't you? Okay? So we're going to practice that right now. So here's a problem about dropping a ball off a balcony. Do you already know how to fill in these energy diagrams? I think you do. I'm not going to do that right now. That's going to be for you to do on your own. Don't forget to go back and do them when we finish the math, though, okay? Yeah. But I am going to help you figure out how to do the math part of it. So here we go. Paris drops a 2-kilogram ball 4 meters off the balcony. Draw the bar graphs of potential and kinetic energy. Complete the calculations. The unit of measure for energy is joules. So far, so good? They give you this background information. You have to use the right stuff at the right time. At the top, halfway down, and just before impact. Just like we've done, huh? At the top, what's the mass of the ball? Yeah, in fact, they filled it in for you, didn't they?
Yeah.
But let's just fill it in so we're certain. Does the mass of that ball ever change? So could I just fill it in all the way across right now? I could. Let's see, at the top, how much gravity is pulling on it? Halfway down, how much gravity is pulling on it? At the bottom, how much gravity is pulling on it? Yeah. Do you have to memorize 9.8? Not really. I don't expect you to. But we use it so much, it shouldn't be too hard, huh? Now, if I gave you one of these math problems, but we were on the moon, would you still use 9.8? No, you'd use something like 2.1 because it's less on the moon than here. Next, the height. What was the height at the top? Hello? What was the height?
4 meters.
Yeah, it started at 4 meters, didn't it? In fact, it filled it in for you, didn't it? Halfway down, what's the height?
2 meters.
Well, yeah, should be halfway. At the bottom, what's the height? 0. Right? Now, we have to do some math. You'll need a calculator to find the potential energy at the top. Which equation are we going to use for potential energy?
N times T, or times H, MVA.
Yeah, you don't have to memorize it. You just have to pick the right one. I believe it's the one that says potential energy, huh?
Okay.
M, what's M? What's G? What's H?
Height.
2 times 9.8 times 4. What do you get? Two times 9.8 times 4?
That for the top.
That was for the top, yeah. We'll come to that, but it is velocity. That's the hard one. Two times 9.8 times 4, MGH. Yes, I did. Okay, are we good with that one? I'm not going to announce the answer because I want you to have it for yourself, all right? Should be less than 100 though. More than 50. Next, at the top, what's the kinetic energy? At the top, before we drop the ball, it must be 0, right? So that one should be obvious. What I want to do now, this bottom V is velocity, but that's a tricky one. So I just want to do all the PEs and KEs first, and then we'll come back to the velocities, okay? Sound good? All right. So let's go to the halfway point. How are you going to find the potential energy halfway down? What was our total energy? Wasn't the total energy the same as the potential energy at the beginning? Does that tell you what to fill in over here on the side? Did you do this already? At all positions, PE plus KE equals how much? Did you do this already? Whatever that is, oh, I don't want 100 because you would be right if you said 100%, but notice it's asking in joules. Yeah, I want the answer in joules. So those two should be the same, shouldn't they? Hey, wait a minute. If that's true, could I then, well, it doesn't actually ask for that anywhere, does it? Okay, never mind. At all positions, we should have the same total energy, which was all potential at the beginning, huh? 70 something? Yeah? Okay. So how do I find out my potential energy when it's halfway down? Take that same number and divide by 2, huh? Or you could do what?
Take the potential energy from the middle.
Yeah.
It's the same.
I wanted to point that out, so thanks for reminding me. So the easy way to find these answers, since we know it's 50-50, you just divide that first potential energy in half, huh? And that's the answer for both potential and kinetic. Are we okay on that? But let's double check our work. Please put in your calculator 2 kilograms times 9.8 times 2 meters, and you should get that same answer again. Did you get that same answer as the original number divided by 2?
You want me to?
First of all, I want you to take this original number, the potential energy that we had, and divide it by 2. I want you to remember that number. Then I want you to go 2 times 9.8 times 2, because that's its new height, huh? It still has the same mass, but it's fallen halfway. And you should get that same answer both times, huh? Does that increase your confidence that you did the right thing? When they support one another, when the answers come out the same, even though you took a different approach to finding the answer? That should make you more confident in your work. Can you fill in PEKE for the bottom by yourself? What do we know? At all positions, it's this, correct? What percent of it is PE when it hits the ground? Now it says top, that should say bot right there, I think, huh? What percent of it is kinetic energy when it hits the ground? Well, it's all kinetic, right? 100% is kinetic. Good with that? Can you fill these last 2 in by yourself? Yeah. Wait for this last thing. Okay, velocity. This is the tricky one. It's a full-on raptor, a velocity raptor. So, actually the first one you can reason it out in your head. We haven't dropped it yet, have we? So how fast is it falling at the top? It's not falling, therefore its velocity must be 0. That one you can just think about. No, it's in meters per second. or miles per hour, right? A distance divided by a time, meters per second. But the other two, we actually have to do some math, and it's a little bit of tricky math. So, watch how I do this. Let me see. I'm gonna just do it on a blank page down here. I'm just gonna use this blank area to show you what I got going on. So as I recall, the equation for kinetic energy, and you can check at the top of your page to see if I'm right, is 1/2 mv squared. Right? 1/2 mv squared. Now what I would like to do is isolate the v by itself. I'm trying to get velocity, but this is velocity squared times m times 1/2. So I have to do some algebra here to rearrange the equation. And I don't expect you to do this on the test, so I'll do it for you. But I just want to show you how I did it. So maybe you remember, if I have 1/2 on one side and I want to get rid of it, I have to multiply by 2, don't I? And then once I've done that, I should be able to cancel that out, huh? Are you with me?
Yeah.
So I can now cancel the 2, I can cancel the 1/2, but if I multiplied one side by 2, don't I have to do the other side by 2 also?
Yeah.
So my new equation says 2ke equals mv squared. Right? What's the next thing? If I want to get v by itself, can't I just divide both sides by m? Which would cancel this side. But if I did one side by m, I have to do the other side by m. Does that make sense? But wait a minute, I'm trying to get v all by itself. How do I go from v squared to v? I have to take the square root, don't I? Yeah. So my final answer, 2ke over m rooted equals my velocity. That's my equation that I need to use. And that's just algebra rearranging an equation I already gave you. Okay, so this is what I think you should do. Since that equation hasn't been given to you on this worksheet, let's write it down right over here. V equals 2ke over m. Except it's the square root of ke over m. And I don't think there's an easy way to put in a square root. We just have to use a pencil and draw it. So add that to your paper so you have that to use later. Velocity equals the square root of 2ke divided by m. So here's how we calculate that one. Take your ke from the middle here, put it in your calculator. For this problem, you work from the inside out. So you start by putting ke in your calculator. Now take that ke and multiply it by 2. Then divide by the mass. Which, for this problem, it's a little weird because that's also 2, isn't it? Should bring you right back where you were before, huh? Now you have to find the square root function on your calculator. If you're using your phone, you got to turn your phone sideways. Remember, the square root is the number that times itself gives you the number you started with. So like, the square root of 25 is 5, because 5 times 5 gives 25, right? Square root of 36 would be 6. You had 39 in there, huh? So your answer should be a little more than 6. That's the velocity for the middle. 6 point something meters per second. Okay, so try it again. What was the kinetic energy? It should have been 39 something, right? Times 2. But then we're going to divide by 2. Then we're going to take the square root and make sure some calculators also have a cubic root. Don't use cubic root, use square root. You should get 6 point something meters per second. Can you do that last velocity problem for yourself then? Take that same approach. The new kinetic energy at the bottom times 2 divided by the mass, which was also 2. And then you take the square root.
I'm only 12.
Were you about 6.6?
That looks right to me. It should be slightly less than 9.
When I hit that
6.
12.5.
The first
No,
one.
you and you do it.
For the middle one, right? What's the
Right
right
there.
That's good.
Oh, wrong, down, I just pressed the wrong button.
This is the moment.
No, just,
And then it's just comes back, right?
no, just watch mine. 30.
This is 0.
How are we doing? Are you getting less than 10 for that answer?
And then square root of 78. I've already done the next one. These are actually easy. This one just goes all your time.
No, I just assumed.
Then I'd like you to go back and color in those energy bars for that problem we just did the math on. Where we let go? So how much kinetic energy? And how about its velocity?
Ladder 9 meters high, so.
Don't worry.
Mass right here. And then 9.8. Yeah. You do the exact same thing for this. As you did that one. And then when you come to the square root.
Vin Diesel. Vin Diesel.
Yo,
Good, and then I was just saying.
who's complimenting him?
It's the one with the 2.
Velocity's the hard one. This number.
Oh, you got it.
And the equation I put up there in red. Multiply by 2, see where it says 2 KE?
Alright.
Equals. Divided by M, and the mass is also 2. So strangely, we're back where you started. But wait.
Yes, Mr. Allen.
That's not bad.
Oh, thank you. They thought the theater calculator, right?
How much potential is there on?
Yeah.
The moment you finish it,
Oh,
yeah, it's a home game.
Like home, like.
I
like shit. I know what you mean. Take the 10 shot.
I'm not seeing.
I'm sitting there on my computer.
Let me see here. Are you an Android?
I heard.
Really don't want to do a Saturday though.
Oh, that's what it is.
Oh, yeah, we're going.
There you go. What are you gonna do this day?
Where are we going today?
I don't know. 39.2.
I think this Wednesday.
I love how Dave kicks.
Got it?
They could square root out. There you go, there.
Next one would be a square root of 74.
Yeah. Yeah. That's what it takes for. You're lost on this one? Have you seen the videos that I posted? That might be the first thing. Right now, I'm recording this class.
Dude, the whole night, he was sitting by himself on his phone. Like 3 minutes every like 2 hours. Literally go say hi. And then that's it. He didn't talk to anyone at all.
One of my classes. Your brother, JT, how long you wanted to go there? Because before
Dude,
left,
he
you were
asked
talking
to go,
about it.
bro.
You said, well, no, he wanted to go. I was like, bro, why are you in high school for any more? Out of high school, he's like, honestly,
Let's change to try to control 75.
Yeah, and then
So what you're gonna do
He
is
wanted
this
to
one,
go.
right?
We're in
One.
Dragon.
So,
Dude,
and
poor JT, I felt how he wasn't talking to anyone. I felt so.
help with Unit 2
I wanted to go
Part
talk. I wanted to
4.
go talk. for 10
This
minutes.
was Thursday's class. Okay? And then I'm gonna put Part 5 on there. So I want you to start with those videos. And that way you can kind of skid through stuff to see where you need help and where you're doing okay. Then, if that's not good enough to get you.
JT probably had a shit. So close.
Yeah, I skipped ahead.
Good.
Well, I mean,
Because like, can I look at the problem? 2 grams again.
I was supposed to sleep at his house.
Two.
The time I know it's like 12:30.
Oh, no, that's number 1.
And I'm like, dude, I think we should crash instead. I was gonna. And then my dad was like,
So you had
literally called me
9
like
meters.
10
Yeah,
minutes.
it's 2 kilograms.
He fell down again.
Yeah.
And then,
Wish it wasn't 2.
9.8. So
Fucking 10 out of 10 photos. He was also up. So my cousin lived there.
5 times.
Oh, yeah, I made it trickier here.
He was like, we got home and just started talking for like 20 minutes. It's like the
I think that
Let him
PD
do
switch. It's 75%.
Oh, 75% up there. I'm thinking 75% below 75.
I mean,
Yeah, you're absolutely right. It's like-
I saw some stuff to set.
Other than that, it should be good.
That's
Velocity, I can't do in my head.
It's just square root.
Yeah.
That's right here.
Like,
Well,
But now it's
yeah,
gonna
you're
get
gonna have to change that.
Yeah.
This one you won't have to change.
that's what I'm thinking. That'd be dope. And
Hey,
then,
you
like,
guys! Come on back. What do we have, 10 minutes?
Put just a minute.
Yeah.
8 minutes.
So, guess what your homework is tonight?
To do the bottom part of that.
Yeah, but I want to warn you. I didn't realize this in my last class and they didn't get the warning. So if you see them, give them this warning. Look at that.
5%.
Instead of taking half, you have to take 75% of the original height, huh? Instead of dividing by 2, you have to take 3/4 of it, huh? 75% of it. So remember a little while ago, we did it with 48% and we did it with 62%. You just go 0.75 times that total energy that you calculated before you dropped it. Do you get the same answer if you divide by 2 as if you multiply by 0.50? Take a number, 10. What's half of it? What's 10 divided by 2? What's 10 times 50%? What's 10 times 0.5? They're all the same, right? So if I want 75% of 10, you have to go 10 times 0.75. Okay? So for this one, for the halfway point, to find your PE, you got to go your total energy times 0.75. Right? Be careful on that one. Okay, get some more work done before we leave. Definitely get these colors filled in on these boxes. You could color in these ones as well if you like. You could save the homework, the math for homework. If you get stuck on any of the math, come see me first period, right? And I'm gonna stop my recording now.